So in the energy applications, we're really looking in terms of improving the engineering of these science and technology areas. So most of them correlate directly to things like efficiency and dollars spent. So for example, in wind energy, the application is attempting to do highly detailed models of entire wind farms, which has never been able to be done before, in order to optimize the operation and efficiency. That results in longer uprates, more steady stream of power, lower operating costs, more efficient wind turbine designs. All of that ultimately translates to dollars. In a sense, when we're looking at moving things to exascale, we went from a paradigm regime where we had just large machines that had you could almost think of them as a quasi-infinite array of single type processors. From there, we went to Titan, which kind of was a transition machine, which introduced the idea of heterogeneous computing, in which case you had series of standard kind of historical processing technology, albeit faster than the previous generations, but combined with offloading accelerator technology, in this case the form of GPUs. As going from Titan to Summit, we've gone from a ratio where on Titan nominally 60 to 70% of the floating point processing power was on these accelerated devices. We're going into Summit where we're at more like 92%. Ultimately, when we get to Frontier, it's going to be some percentage higher. We don't know exactly what that's going to come in at. The bottom line is that to get performance, to be able to realize the vision of being able to do these really large simulations, you actually have to do more and more or offload more and more important work in the calculation to the accelerator devices. You can't just use the onboard host CPUs. And able to do that, we've been able to use kind of like this stepwise progression. So it's like, think of it as a swimming pool. You kind of dip your toe in with Titan. You start to swim into the place where it's a little harder to stand in Summit, and then in Frontier, we're going to be in the deep end. But it's usually dangerous to learn to swim by getting thrown into the deep end right away. We're seeing right now, basically, all of the applications in ECP to varying degrees are starting to get up and operational using the accelerators, not just having their code on them and running, but actually starting to get performance. So for example, in the nuclear energy application, we're already seeing something like a factor of 20 to 40 times improvement in terms of the ability to run a calculation faster. So in that case, we're able to run the same type of fidelity physics in a 40 times faster rate. What that means is you can actually refine parts of the problem much more and still be able to turn around a detailed calculation in a time that might have taken Summit, a year of runtime on Titan. We can do that, in order 2 weeks on Summit. But now you're getting into the range of feasibility where you actually can do real investigations as opposed to just kind of one really long scale calculation. And as I mentioned, these are more engineering scale applications. Engineering applications means you have to run lots and lots of simulations. So running one big calculation in a year doesn't really get you anywhere. The build workflow throughput times of what people want information on is much faster than that. So you need to get these things down. Nominally, we'd like to be able to do really useful work on large calculations on something on the order of like 6 to 8 hours, and we're actually starting to see that now with Summit, or with the potential of doing that with Summit, and ideally with Frontier, we should be able to get there with another factor of 7 to 10 improvement, assuming we can continue to scale in the right direction. It means that we can do calculations of the like we've never seen before into something like 4 to 8 hours, and that's actually very reasonable, because when you think of in many cases, when you're doing big validation or verification simulations, of which these are the type, you would do is it's the kind of thing where you set something up to run, you go home, you come back the next morning, the simulation's done, and you spend the day analyzing it, doing more perturbations, and then you can on that workflow, you can actually get a lot done with that scale calculation. It's much harder when you're sitting there thinking, oh, I've got to wait 2 weeks, a month. 6 months is kind of out of the question. You might do that once, it might provide some value, but certainly in the science application domain, like cosmology or even climate, running a simulation for 3 months is something that's reasonable, because that's more of a discovery science type of application, whereas in a more of an engineering science application, where you're trying to have some feedback into the design, prototype, build process, it needs to be a little bit faster. Right now, for example, I'm going to go back to the wind application. Right now, what they're looking at, nominally, they'd like to be able to do an entire wind farm. So you have, say nominally something on the order of 50 windmills, turbines plus towers spanning a 1 kilometer by 1 kilometer area. That's a really big problem. Right now, they're starting to get to the range where they're looking at doing something like on the order of a 3 by 3 array of turbines. Okay, so that's 9. Okay, so something like you want to actually expand that and be able to run the same type of calculation or simulation and get that same high fidelity information, but do it on a fully operating wind farm. That's the kind of jump you make by going from something like Summit to something like Frontier. With the advent of Frontier and AMD coming on board, we're moving into more what I would call program portable type semantics, where, for example, HIP is ideally going to be a more general application programming language that will be a lot more useful for codes to go to, because then you're not going to be confined to one architecture type. So in addition to being suitable for running on Summit or on Frontier, it should also have applicability to other platforms and other machines. And as excited as we are about Frontier, none of us are envisioning that this is the only machine we'll ever run on, right? So the ability to both be able to run and write optimal code for Frontier, but then be able to immediately turn that around and apply it to all sorts of different architectures is actually really interesting. And I think Frontier coming here is kind of driving that migration. If we keep having the same vendors over and over again, it becomes very easy to just have kind of very platform-specific programming environments persist. And by having multiple ones, it pushes the community into this more, into developing these more general purpose programming tools. And that's only going to benefit the computational science community in a broader sense.